Welcome to AP Chemistry at Hananita High School. Today in notes we'll be looking at really part 2 of the Chapter 14 notes that deals with Section 14.3. Section 14.3 really looks at the effect of concentration on rate. So today we'll be looking at the effects between those two things, and that's really an extension of what we looked at yesterday. Now what we're actually doing here is what's known as finding the differential rate law. It's one of the major things we do in the chapter is differential rate law. And what we're going to do is establish the relationship between how concentration changes affect changes in the rate of the reaction. Now, one can gain information about the rate of a reaction by seeing how the rate changes with changes in concentration. To simplify the math, one of the assumptions that we're going to be making in this chapter is that we will always use initial rate data. And this is really the instantaneous rate at time zero when finding the rate law. So you'll notice in the data tables that we look at with this section that it'll always mention initial rate. And that's basically the instantaneous rate at time zero for the reaction situations that we're looking at. And this is something that most of you did last year in honors chemistry. If you're coming from regular chemistry, this is one of those things that you've got a little bit extra to learn, because what we're really going to talk about today is something that most of you did last year in honors chemistry. Now here's a typical set of data that we're going to see in the chapter, and in particular when we're dealing with differential rate law. Whenever you're doing differential rate law, you are always going to have concentration data, and notice it says initial concentration, and initial rate data. So notice it says observed initial rate. And one of the things you want to pay attention to is what types of data we're dealing with. Notice their concentrations we're dealing with molarity situation here, so actual concentrations, and a rate would be a molarity per second. You always want to take note of what our time unit is when we're dealing with things. So the first thing you should always do is evaluate what's in your data table. So understand what the data is basically showing. The other thing you'll see with this, although it's not always there, is experiment numbers. And that's so that we can quickly zero into what set of data we're looking at. So when I say experiment 1, you know you're looking at this set of data right here. Now the reaction we're looking at in this particular case is the reaction of aqueous ammonia with aqueous nitrate ions to make N2 gas and H2O liquid. So here is the balanced equation for the reaction. Now one thing to be careful of, while rates in what we looked at yesterday with relative rates between two things, the stoichiometry plays a role, be careful in just thinking that what we're looking at today with rate orders, the exponents in our rate law expression, our differential rate law expression, are really just pulling up the numbers in the coefficient spot in our balanced equation. Sometimes they are, sometimes they aren't. So really this has nothing to do with the stoichiometry of the balanced equation. What we're really doing is looking at our experimental data. So if you take a look, it says if we compare experiments 1 and 2, we'll see that when NH4 plus doubles, the initial rate doubles. So what you basically do is pick two experiments where one concentration is being held constant. So in experiments 1 and 2, our NO2 minus concentration is not changing, which means it's not going to have an effect on the rate. So everything that happens to rate is directly caused by what's happening here with ammonia. And in these two experiments, in essence, we went from 0.01 concentration to 0.02. So when we doubled our concentration, look at how these two things compare. They're doubled. So doubling the concentration doubles the rate. And what we're really doing here is using experimental data to understand how changes in the concentration of a particular reactant can have an effect on the overall reaction rate. Now likewise when we look at experiments 5 and 6. So now we're doing these two sets. Notice these are constant. And once again, a nice simple situation, these double. Always look for double because the math is so much easier. We can find it in other ways, but the math is a whole lot easier when you're dealing with a double situation. When I doubled this concentration of NO2 minus and the NH4 was constant, notice what happened to the rates? It essentially doubled. So once again, we can see doubling the concentration of one thing when holding the other constant cause the overall rate to double. And what we're really doing here is establishing relationships between concentration and our final rate. Now, what we basically said was doubling the concentration of NH4 doubled the rate. That means that the rate is going to be proportional to the ammonium concentration. Doubling one, double the other. That's a proportionality. Now, we also noticed that when we doubled the rate of NO2 minus, or doubled the concentration of NO2 minus, we doubled the rate. So the rate is also proportional to the NO2 minus concentration. Well, if the rate is proportional to both of these, then the rate would be proportional to the product of those. So therefore, the rate of the reaction is going to be proportional to the concentration of NH4 times the concentration of NO2 minus. Now, what we're going to end up doing when writing a differential rate law is write that as a rate expression. So right here would be our rate law or rate law expression or differential rate law or rate law expression. There's a lot of different ways we can say the exact same thing. But the rate of this reaction would equal some constant K, because remember, when something is proportional, it differs by a constant. And this time we're going to call that constant a lowercase italics k. That's our rate law constant, times the concentration of NH4 plus times the concentration of NO2 minus. So that would be our rate law expression for this reaction. Now, this is something you did last year in honors chemistry. So what I just walked you through is something that most of you did last year. So this should be looking familiar. And this equation is really called the rate law, and K would be the rate constant for the rate law expression. So what we just established was rate law, and the K is the rate constant. Now, rate law shows the relationships between the reaction rate and the concentration of the various reactants in the equation. The exponents are what are called the order. So in the last problem, doubling one doubled the other, well, that would be an exponent of 1. So the concentration to the first power equaled the change in rate. So order is looking at really the exponents in our rate law expression, because when one thing doubles, the other might double, or it might quadruple, or it might be 8 times bigger. So it's an exponential comparison. Now, since the rate law for this reaction turned out to be that, so the rate equals K times the concentration of NH4 plus times the concentration of NH2 minus, it's first order. Both of those would be 1s. First order with respect to NH4, and it's also first order with respect to NO2 minus. So one of the terminology phrases that you'll need to get a handle on this chapter will be the idea of first order in, or more importantly, which is typically see this as, is first order with respect to. So the rate of this reaction is first order with respect to NH4 plus, and it's also first order with respect to NO2 minus. So the order is really the exponent that you put in the reactant concentration and see how it affects the rate. Now, the overall reaction order is really the sum of the individual exponents. So while this reaction was first order with respect to NH4 and first order with respect to NO2 minus, the overall, the total order, would be a second order reaction. So it's first order with respect to these two, second order overall. So be careful when you're talking about reactant orders. It's either looking at the exponents of the individual reactants, or it's looking at the overall exponents. In this case, they would have an overall order of 2. Now, what does the rate order really mean? Well, it's really the power you have to multiply your concentration by to see how it affects the rate. So the change in concentration has no effect on the reaction rate. Now, this is very rare. It can happen, but we just don't see it happen all that often, unless they're making it happen on the AP test. That's where you see it more often, is there. That would be known as a zero order situation. So if changing the concentration had no effect on the rate, so doubling the concentration had no effect on the rate, so let's say we have a really simple reaction here. Rate equals K times a single concentration A. If doubling A did nothing to change the rate, that means it has to be zero order, because A to the 0 power is always going to become 1. So if it's a zero order relationship, doubling A had no effect whatsoever on the reaction rate. The reaction rate is independent of that concentration. What you'd be left with is this is going to equal 1, so you'd end up with rate is going to equal the rate constant K. So in a zero order reaction, really rate equals K. Now, in a first order reaction, the rate is directly proportional to the reactant concentration, which means doubling the concentration doubles the rate. And these are really common. In fact, most often you're going to see first order things. Our whole nuclear decay chapter, chapter 21 that we did back with chapter 6 and 7, the kinetics of the reactions we looked at, all of those were first order kinetic reactions. So we've seen first order reactions before. Decay rates are an example of that. Now, if it's first order with respect to A, that reaction would look like this for the rate law expression. So we could write the rate law equals K times the concentration of A to the first power, or you could just write it like this. Normally, we don't put the 1 there unless I want to put it there for emphasis. So you'll sometimes see me do it, but you never really need to. First order, that's assumed that you know that A would be first order written like that. So basically, doubling A would double your rate. That's a first order relationship. And that means to the first power. Now in a second order relationship, doubling the concentration would quadruple the rate. So that means it's a squared situation. Now if it was tripled, remember we look for double because they're easier math, but sometimes you don't have a doubled situation. So if the concentration has been tripled and it's second order, that would mean 3 squared, it would be 9 times bigger. So in a second order situation, you're typically seeing something doubled or tripled. Well, doubled would be 2 squared, 4 times bigger. Triple would be 3 squared, 9 times bigger. So that's what you look for to identify a second order situation. So keep in mind, rate law expressions are found from experimental data 100% of the time. That's where we get them from. They are based upon experimental evidence. Otherwise, there's no real way for us to determine what the rate orders are, except to look at what the data tells us. Now, written as a rate law expression kind of depends here because now we're talking about more than one. So it could be a situation where we only have K and it's second order with respect to K, or it could be a situation where we had 2 different substances, A and B. So both of these would be overall second order relationships. But in terms of the doubling quadrupled, that would be looking at with respect to A. We'd be looking at when A was doubled, not the total concentration. That makes it a lot harder to look at the products of things. So a second order overall could look like either of these two things. First order with respect to A and with respect to B, second order overall total, or it's second order with respect to A. Now to find the rate law, you basically have to have concentration and rate data. So if you ever see a data table and you look at the data table and you see it has concentrations and it has initial rates, 100% of the time you're going to be doing differential rate law stuff. You're going to be deriving the rate law expression and maybe calculating K. So the rate law expression generally depends upon the reactant concentration. So you're going to be zeroing in on how changes in the reactant concentration affect the initial rate. You can see a catalyst sometimes in these, but you're never going to see that on the AP test. You're never going to see it in class. So basically what we're going to be doing is looking at just the reactants involved in the reaction. And what you need to understand is there's no other way to do this. We have to have experimental evidence. So either you're doing an experiment or they're giving you concentration and rate data every single time. So if you see concentration and rate data in a data table, you're going to be looking at the differential rate law. Now keep in mind, when you do this, you can have orders where the exponent would be 0. That's rare, but it does happen, particularly on the AP test. You can have fractions. That's very rare. I don't think you're ever going to see one in class or on the AP test. So it could be a 1/2 order. That just means square root. That can happen. But usually you're going to see 1 or 2. So 0, 1, or 2 are the things that we're going to see from time to time based upon our experimental evidence. So here's an example of what we're looking at. And you're going to do some examples here in the homework. We're going to also practice some examples tomorrow in small groups because this is the type of thing you've got to get to the point where you see exactly how to do this. You've got to understand it. Okay, consider the gas phase reaction between nitric oxide and bromine at 273 degrees Celsius. The balanced chemical equation is 2NO gas plus Br2 gas yields 2NOBr gas. It's a reaction we've actually looked at previously in the notes. The following data for the initial rate of appearance of NOBr were obtained. So notice they're giving us initial rate data with respect to NOBr. So at the beginning, experiment 1 here, we had an initial concentration of 0.1 NO and 0.20 for Br2. And what we did was we basically carried out the experiment and we calculated what the initial rate of appearance, or the instantaneous rate of appearance at time t equals 0 was for NOBr, and we determined that to be 24 molarity per second. So that is our initial rate of NOBr. Now, in essence, we don't really worry about that. What you need to know is these are our concentrations, and that's the initial rate. In experiment 2, notice you've got a different concentration for NO, but you have the exact same concentration for BR2. And notice this is our new rate. And then you also have data in experiment 3. Notice NO is constant and BR2 is changing. And then finally in experiment 4, the NO is unique to all the experiments, and the BR2, well, it's different than 1 and 2, but it's the exact same as 3. So we've got a number of different situations happening here. Now what we want to do is, through understanding table, which is looking at the relationships on the table, sometimes that's called table logic, or by doing some fundamental algebra. In this case, we're going to be stuck with doing it the ugly algebra way because we don't have simple double relationships here often enough to just do the problem by simply looking at the table and looking at doubling type situations. So this is a little bit trickier data than the previous one we looked at. Now, the first thing I want you to do is determine the rate law, which is, remember the rate law expression. Rate equals K times the concentrations raised to some power. So what we're really looking at here is going to end up with something like this. Rate is going to equal K times the concentration of NO raised to some power times the concentration of Br2 raised to some power. Our job is to find out what's in this spot where those question marks are to get our rate law expression. So that's really where we're going with this. Now, to go about doing that, first we're going to zero in on NO. Now, we want to pick a situation where something is constant. Well, if I want to look at what's happening with NO, find out NO's order, then I want a situation where BR is not changing, because if it's changing, it complicates the relationship. We want to keep it simple, so keep it simple. KISS principle here. So BR is staying constant at 0.2. The problem here is we just didn't double NO, and that makes the math just a little bit harder, because the math is easier. When you double this, did you double that, or did you quadruple that, or did it have no effect? Those are the situations we're going to be seeing. Well, we didn't just double it here. So we're going to look at the ugly algebra way to do this. Now, it's not very hard, but it's simpler. It's nowhere near as simple as, okay, look for doubling relationships inside the equation. So in this particular case, if you look at what happened, we started at 0.10 NO, and we ended at 0.20. And we started at an initial rate of 24, and we ended up at 150. Now, to simplify the math, I'm going to put big numbers on top. What we really did here in this expression was this relationship. So I'm going to show you really where that comes from. Now keep in mind, the rate is going to equal here K times the concentration of Br2, and there's a reason why you'll see in a second I'm putting this one first, to some power, we just don't know what that power is, times the concentration of NO to some power. Now, I want to get rid of that question mark up there, because the order is not going to change. Once we've established what the order is for Br2, what its exponent is, it's not going to change. So I'm just going to say Br2 is going to be an X here, and that's not going to change. Now remember, what we have here is the rate equals K times the concentration of Br2 to some power times the concentration of NO to some power. And once again, the NO doesn't change, so I'm going to get rid of my unknown there, and let's just call that the Y. Now, those two things are equal to each other. Now, what you do to one side of an equality, you have to do the other, and you maintain the equality. So what I'm going to do here is divide them both by the exact same thing. Now, the rate of another experimental situation is still going to equal K times Br2 to the X times NO to the Y. So the top reaction would be the reaction rate from one thing's perspective. The bottom would be the reaction rate from another thing's perspective. Those two things are equal to each other. So if I divide both by the same thing, I maintain the equality. Well, look at what happens in this relationship. K's are the same. They're going to cancel. Br2's, remember, were constant in experiment 1 and 2. They were constant, both 0.20. They're going to cancel. What we're going to be left with is The ratio of one situation over the other situation equals the rate of one over the other. Now, the way I set it up so I had big numbers on top is I put experiment 2. So notice it's the 150 that's on top, and that would be 0.25 to some power, x or y. In this case, I left it as just the universal constant x here. And then for experiment 1, it would be 24 and 0.1. So I plug those in here. So what I really have after I cancel the other stuff is 0.25 to the x power over 0.1 to the x power is going to equal our 150 over our 24. Oops, 24. Well, 0.25 to the x over 0.10 to the x is 0.25 over 1.0 to the x power. So that's really where I got that from. All I did was wrote two algebra situations here. This one over this one, and then canceled. And what I was left with was that situation. Now, if I take 0.25 over 0.1, I get 2.5. If I take 150 over 24, I get 6.25. So 2.5 to what power equals 6.25? Well, you can just play around with this in your calculator. Remember, it's going to be simple things like 0, 1, and 2. Well, obviously it can't be 0 because then it would equal 1. So try 2.5 squared. Does it equal 0.625? Yes, it does. So the order of NO has to be second order. So even though I didn't have a simple doubled situation doubled, I can see here what the relationship is. So second order would be a double quadrupled. Well, I didn't have a double situation, so I couldn't do that. So I had to really rely upon the algebra of the situation here to really see that it was second order with respect to NO. So if it's not a nice easy double like it is 90% of the time, you can set it up as a simple algebra expression and get the same thing. So that's what it would be with respect to NO. So our unknowns here, NO, that's got to be a 2, second order with respect to NO. Now let's do the same thing with BR. So to understand what the order is of BR, oh, I forgot to mention, if you've got a situation where your numbers aren't equal, like you're doing a real experiment, remember the way to solve this is to use log math. 2.5 to the x equals 6.25. Well, x would equal the log of 6.25 divided by the log of 2.5. So you can reduce it really to an algebra problem by finishing it that way. In this particular case, 2.5 to what equals 6.25? Well, square it and you see it works out, so it was an easier one. If you're using experimental data, it might not be a nice whole number like that. It might give you 1.85 or 1.9 or 1.99 or something. So remember, you've done log math before. You can handle solving for that x if you need to, and that's something we'll review more when we get to a lab. Nice thing about the homework problems, they all make nice and easy zeros, ones, and twos, so that takes care of that. So now we're ready to look at BR2. Now once again, we've got to pick two situations where NO is constant. So if we want to know BR2, we want NO out of the equation. So in this particular case, we're going to look at experiments 1 and 3 because our NOs are constant in those two situations. And you'll notice, once again, oh, it's tricky. It's not a nice simple double. 0.2 to 0.5 is a little more than double. In fact, it's another 2.5 situation, just like it was before. So this is trickier data than you're going to see 90% of the time in problems. So when we set up our expression here, I'm going to put big numbers on top to simplify things. So 0.5 over 0.2 to what power is going to equal 60 over 24. You carry through, and in this case, you'll see it's 2.5 to what equals, sorry, that should be 2.5 equals 2.5. So it's not 0.25, that's a typo. And that means x is going to equal 1 here. So it's second order with respect to NO, but it's first order with respect to BR2. So when you set up the rate law expression, you'd write rate equals k times the concentration of NO squared times the concentration of BR2 to the first power. Remember, you don't have to write the 1 there. I'm just writing it there to make it obvious. So that would be part A, determining the rate law. Now, that's typically the first thing you do with these problems is determine what the rate law is. Well, since I have rate data and I now have a rate law expression, the second thing you're always going to be asked to do is to calculate the rate constant for the reaction. So once you've got a rate law expression, usually the next question they ask you in the homework problem is what is the value of K? What's the rate constant? Now remember, in this case, rate is going to equal K times the concentration of NO squared times the concentration of Br2. So if you want to solve for K, that would equal the rate over NO squared times Br2. Well, we've got a data, or a table, involving rates. So we've got that. We've got NO concentrations, and we've got Br2 concentrations. We can plug in and we can calculate. So if you take a look at experiment 1, so I'm going to call that K1, it was 24, so that's going to go on top, over the concentration of NO squared, so 0.1 squared, times the concentration of 0.20. And plug that into your calculator and solve. Well, we've got 3 other experiments here, so we could set it up for the second experiment, and the third experiment, and the fourth experiment. Now, take a second and think. So let me pause here and allow you to think about this. What do you think is going to be true about our K values? As our reaction proceeds, under different experiments with different concentrations, would you expect the K value to change by a predictable amount or what? Well, think about it. K stands for constant. When we plug in and calculate 1.2 times 10 to the fourth, and units. Remember, you've got to pay attention to your units. The rate here was a molarity per second. On the bottom, we had the concentration molarity of NO squared and the concentration or molarity of Br. So what we're going to end up with here is the molarities are going to cancel, and we're going to have a 1 over S on top and a molarity squared on the bottom. Well, that's the same as 1 over molarity squared S, which is simplified in one line in a lot of books as molarity to the -2, S to the -1. That's a common way to write this. So that's where our unit came from here. We're going to talk more about that in a second. But notice, the K's are all the same. So you really don't need to do multiple calculations here. Pick one set of data. As long as the data is valid, and hint, in the homework problems in the book, it's always good data. Pick any one of the experiments, and you can calculate the rate constant from it. Now, if you're doing a lab, yes, you'd do multiple rates, multiple concentrations, multiple K values, and take the average of them to get your best look at what the K is. But in terms of homework problem, keep it simple, just do one. So the K here is going to equal 1.2 times 10 to the fourth, and it would be 1 over molarity squared seconds, which is molarity to the -2, second to the -1. Another way to write that exact same thing. So remember, these two things are the exact same thing. Get used to how you see units written in this chapter. So that's a typical problem. A is to calculate the rate law expression. B would be to calculate the rate. Now, there is a C here. So that means, what else can we do? Well, we have a rate law expression, and we now have determined the K value. That means we can, if we want to, determine rates at various concentrations. So that's what C could be, is what is the rate going to be at this concentration and that concentration. So that's one thing we could do. But I want to use this as a review to tie in what we talked about yesterday, stoichiometry. So how is the rate of appearance of NOBR related to the rate of disappearance of BR2? We could have answered this question without doing anything else in this reaction, anything else in this problem. So we could have done C first if we really wanted to. This is something we looked at yesterday. So this is just reviewing yesterday's situation. So how are the two things related? Well, they're related through the stoichiometry of the situation. So from the balanced equation, remember NOBR here appears twice as fast as the BR2 disappears because it's a 1-to-2 relationship. So in terms of yesterday's discussion of relative rates, 1/2 the concentration change of NOBR would equal the negative the concentration of BR2 because it's the inverse of the coefficient in the rate relationship here. So if we take half of the concentration of NOBR, that would give us the concentration of BR2. So that would be the relationship between those two things. Now, consider the gas phase relationship between nitric oxide. The following data was obtained for the initial rate of appearance of NOBR. So here's where this particular term is going to be very important. So part D, we're looking at an entirely different type of thing here. It says, what is the rate of disappearance of BR2 when NO equals 0.075 molar and BR2 equals 0.25 molar? So this means the rate law is for NOBR. And this is asking you about BR2. Now remember the relationship here. BR's rate is going to be half of the rate of NOBR. So if we take our rate law expression from the viewpoint of NOBR, remember our rate law expression was rate equals rate, and this is the rate from the data of NOBR with respect to NOBR. The rate of NOBR would equal K times NO squared times BR2. If this is the rate law expression with respect to NOBR, and BR2 is going to be half of NOBR's rate, then plug in your numbers into the rate law expression. That's what I've done down here. I'm using my K, I'm using my two concentrations raised to the appropriate power, and I'm multiplying it by half based upon the stoichiometry. That would give me the rate of BR2. In this particular case, once you cancel out all the units, so molarity squared on the bottom, molarity squared on the top, they cancel, and I'm going to be left with molarity on top, seconds on the bottom. That would make sense. That's what every rate's going to be, is a change in concentration over a time. So that works by units. You'd end up with 8.4 molarity per second. So in D, what we're doing is actually doing something from what we talked about in today's notes, calculating the rate from the rate law expression, and then relating it to what we looked at yesterday. Since the data is for the rate of appearance of NOBR, if we want to calculate the rate of disappearance of BR2, we would do it using the equation we just established and then take half of it. So this problem is really putting together the last 2 days worth of information. Now, the last thing I want to talk about here in notes before we wrap up is units of the rate constants. Now, what you need to understand is the units of the rate constants really depend upon the overall reaction order. So you have to write the rate law expression first. And you need to understand the units of K exist to do one thing: to make the rate have units of molarity over time. That's the sole function of the units in our K value, is, remember, it's rate equals. So when we're calculating the rate, we need to end up in molarity per time. We need to have appropriate units in our K to do that, regardless of what our overall order is. And there's a relationship between those two things. So remember, that's really how the units of K's are derived. It's based upon the overall order. So the units of our rate are going to equal the units of the rate constant times the units of the concentration raised to their overall order. So you're looking at, is it overall first order, second order, third order, whatnot. So if you rearrange this to look at what the units of the rate constants are, you're going to get the units of the rate, remember that's always molarity per second, divided by the units of the concentration raised to the overall order. So if it's first order, we would have our units of rate on top, which would be molarities per second, because that's what it always is, molarity per second. Or I guess it could be per minute or per hour. The data will tell you which time unit it is. And since it's first order, you're going to have, for units of concentration, a molarity raised to the first power. So you're going to end up with an M on the bottom. Well, the molarities are going to cancel, and what you're left with is inverse seconds. So for every, and I mean every, overall first order rate law expression, if the overall order is first order, the units of your K value are always going to be 1 over S every single time. And if it's written as S to the negative 1, it means the exact same thing. Now, if it's second order, remember, it's going to be the units of rate, which are always molarity per second. Now it's going to be over a concentration squared. So this M cancels one time, and you're left with inverse seconds over molarity. Well, that's 1 over molar seconds, which could be written in either of these two ways. So every time you get a second order, it's going to be 1 over molarity second. or 1 over molarity minute, or whatever. But that's what they're all going to look like. Now, what would a zero order situation look like, or any other order after this? Well, third order, remember it was 1 over s for first order. Second order, it was 1 over ms. Third order is going to be 1 over m squared s. Fourth order would be 1 over m cubed s, and so on, and so on, and so on. So if you know what the overall order is, you know what your rate constants units are going to be every single time. It always works out that way. So a simple way to look at this is it's 1 over the molarity raised to, and here's where you have to look at the overall order. Overall order minus 1. And that's going to be times seconds. So all that's going to be on the bottom. So if you know what overall order is, you can quickly see what your units are going to be. Now for zero order, remember in zero order it was a rate equals k type situation. Well, rate is molarity over time. So k has got to be molarity over time. And if our time unit was seconds, then it would be molarity per second. So if you know the overall order, you always know your units of k. And that's where we'll finish off today. So that ends part 2, section 14.3 of the kinetic notes. Good luck with the homework.